Hi, I'm Jai from UT Austin. Welcome to my talk about TypeT5. In this work, we focus on the problem of machine learning-based type inference, where the goal is to let a machine learning model predict the missing type annotations of a given Python code base. Prior approaches for this problem model type inference as a classification problem, where a neural component is used to pick a type from a fixed set of candidates for each unannotated variable. And as a result, these prior approaches have to map complex types into simple types to maintain a finite set of labels. In this work, we instead propose to approach this problem using a Seq2seq paradigm, where we let the model autoregressively predict a sequence of type tokens. This improves the consistency between subsequent type predictions and allows us to predict from an unbounded set of types, including user-defined types and generic types. And we implement this Seq2seq idea using a code generation model called TypeT5. We fine-tune TypeT5 on our type inference task using a masked span infilling objective. For each missing type annotation in the input, we insert a special placeholder token and feed the resulting code into the encoder-decoder transformer architecture. We then train the model to output another token sequence that precisely specifies what type should be inserted at each placeholder location. Instead of just using the surrounding code as the prediction context, type inference is a task that benefits from a more global view of the code base. Hence, we carefully construct the prediction context for each target function using three parts: the preamble, the caller context, and the callee context. The preamble contains import statements and type stubs that shows the model which types are available for prediction in the current context. The caller context contains the code of all functions that potentially use the target function according to static analysis, and this caller code demonstrates how the target function is being used. Finally, the callee context contains the header of all functions that are either used by the target function or used by a function from the caller context. By omitting the function bodies, this tells the model how each used function behaves without overflowing the context with too many tokens. Using this dynamic prediction context and a topologically sorted usage graph, we can then perform an iterative decoding scheme to add type annotations to the entire code base. The first decoding pass goes from callees to callers, where the model decodes the missing types for each function autoregressively. And the predicted types are then inlined into the callee context for later predictions. This ensures that all callees in the context are type annotated by the model's earlier predictions. In the second decoding pass, we let the model make type predictions again, but going from callers to callees. Note that in this decoding pass, both the callee context and the caller context are fully typed. This way, we allow the type information to be propagated in both directions, refining the results to be more consistent. Now, let's see some results. Here we compare TypeT5 with three other approaches taken from prior work. As you can see, TypeT5 not only outperforms all other approaches on common types, but it also more than double the previous SOTA performance on user-defined types. We also performed ablation experiments to study the impact of the prediction context. We found that removing any proposed part of the prediction context can lead to worse performance in terms of both accuracy and type error count. Lastly, we also compared the performance of following different decoding orders. The results show that our proposed two-pass decoding strategy performs the best, and it especially improves the type error count, suggests that having a second decoding pass is crucial for improving the overall type consistency across the code base. We also see that a bad decoding order like caller to callee can lead to worse performance than just following a random decoding order. To recap, we proposed three key ideas for applying pre-trained transformer models on type inference and showed significant improvement over prior approaches. Please check out our paper for more details, and feel free to reach out if you have any questions. Thank you for listening.